Newcastle logo off the slides. So the background to this was that at Newcastle I used to give a talk on the history of programming languages to our first year students as part of the social impact of computing strand that we had in our curriculum as required by the BCS as part of the professionalism. And we thought they should know something about the history, and so I gave this talk. And I thought it might be an interesting thing to present here, so I offered it to Jeff a few years ago, and he said, "Oh well, that's all very well, but you need to put some stuff in about what's happening in now and in the future." And I thought, that sounds like hard work. Maybe I won't do it after all. But then a couple of months ago, I was at a very interesting talk here, where somebody was talking about the NoSQL databases. Okay. So all these new ideas about, who needs relational databases? Let's have network databases instead. Let's have document-based databases. And I thought, this all sounds a bit familiar. When I was starting out, relational databases were the new thing, and network databases were the standard thing. And there's a definite feeling of deja vu here, and people have maybe forgotten all the reasons they switched from network databases to whatever. So that gave me the idea for the title of the talk, Back to the Future, the history of programming languages. So it was in the context of databases. I thought all these people inventing NoSQL databases should perhaps go back and look at the arguments around the time of the 1970s when relational ones came up. So the idea is, what can we learn from the history of programming languages? Are we still seeing technical innovation after 50 or 60 years of evolution? Or is there nothing new under the sun? Ecclesiastes was a bit of a pessimist, okay? He wrote that 2,000 or 3,000 years ago. So maybe there's been a few new things since then, but he was very pessimistic. And in particular, if nothing new, are there new things happening, or what can the past tell us about the future? So I thought it'd be interesting to give a talk about some of the key arguments and debates that have informed the development of programming languages and speculate about future trends. So that was the abstract I wrote for Jeff. And of course, when I came to write the talk, I realized this was an absolutely mammoth undertaking. I couldn't possibly cover this vast subject. But I hope I can be entertaining and talk around this a bit. So if you're expecting me to give you a fully formed analysis of all of this. Anyway, so I thought it would be good to start by putting it in context by telling you a little bit about my own personal programming history. So my first programming language. Then I'm going to give you the sort of panoramic perspective on how I think programming languages have evolved. Then I'm going to mention a whole load of technical issues, each of which I could give a talk about, and then I'm going to talk about a couple of them, and then speculate a bit about the future. So, real programmers don't eat quiche. Okay, I don't know if anyone remembers those quotes. Okay, I can't claim to be a real programmer, but I was a pretty real programmer, as real programmers go. I'm not old enough to be a really real programmer, and I do eat quiche. So. But anyway, when I was a lad, the traditional thing, when I started programming, we didn't have any of these sissy icons of Windows. All we had was zeros and ones, and sometimes we didn't even have ones. Database program using zeros. You had zeros, we had to use a letter O. I'm sure this is striking a few chords. So here are the real program quotes, and there's tons and tons of them on the internet. And this is one that I remember from when I was a PhD student. Okay, real programmers don't write in Pascal or Bliss or Ada or any of those pinko computer science languages. Strong typing is for people with weak memories. So those arguments about dynamic types and all that stuff, they're not new. They've been going on a long, long time. Okay. So I was a Fortran programmer. Okay. So I started Fortran, and so this is. I used to have boxes of these up in the attic until my wife persuaded me to throw them away. I know, terrible. So you know what these things look like. Fortran was interesting. So you can see that there was actually a structure here. So the statement went from column 7. The statement number went in columns 1 to 5. I think it would go in column 1. Column 1, if it was a C, meant it was a comment. Column 6 was for continuation, and column 73 to 80 for if you drop the deck of cards on the floor. You put a sequence number there so you could sort of shuffle them and get them in the right order again. So, of course, if you accidentally type code with that margin, anything you put there will be ignored, which would cause some interesting syntax errors. This is more or less the first computer that I programmed on. It was in 1130. It had 32K of memory. The Fortran compiler ran in 8K. I mean, I don't know what Bill Gates thought when he said that 640K was enough for anyone. I mean, this is a proper Fortran compiler. It ran in 8K.
My first computer had 4K. So
yeah.
One up there.
400 cards a minute. That sounds quite fast to me. Anyway, I don't know. But this was real batch processing. Okay, you put the cards in the card reader, which was on one side of the room, and then you went across to the printer on the other side of the room to see what the output was. And I did that, and there was a console in the middle, but you know, it wasn't interactive. You know, I did write a noughts and crosses program once because there were 10 console switches. Okay, so there are 9 squares on a noughts and crosses board. So the idea was, you know, you'd flip a switch to indicate your move, and the line printer would spit something out, and you go and have a look and see what it does. Flip another switch. And of course, the program was buggy and went into an infinite loop. But fortunately, I thought to use the 10th switch as a sort of get out of jail card, so I was able to get out of it. But that was the sort of thing I was doing earlier on. I was 14, okay, I was at school when this happened, and I'm talking 1973, 1974 sort of time. So this is the Fortran program. This is the kind of thing I would have written, so you know, it's kind of mathematics, so this is solving quadratic equations. Here we've got the infamous arithmetic if statement. Okay, so we calculate the discriminant and then we say we branch 3 ways depending on whether it's negative, 0, or positive. Okay, can't do that in modern languages. You know, Fortran had a few tricks up its sleeve. So we went 3 different ways on the discriminant and decided what to do. And then here's the main program, which is calling the routine and then printing out a few statements and so on. And there's a bit more on the next slide. One of the interesting features of Fortran was that white space was not considered significant. Okay, so you could have the names of variables with spaces in them. So you could have a variable called average of x and average space of space x. Would be the name of the variable. Characteristic of Fortran was that you didn't have to declare variables. So bits of punctuation by mistake, things go wrong. And there's a classic story, I'm sure you all know it, but just in case you don't, in Fortran you would, that's not a very good colour. In Fortran you would write a loop like this, I equals 1, 10. Okay, so that would be some stuff, and then we say 10 continues. So that would be a for loop. And legend has it that, you know, if you put a full stop there by mistake, so you have a typo, that's perfectly valid, but now it's an assignment to a variable called do10i. Okay? And legend has it, probably incorrectly, that mistake caused the Mariner Venus satellite to crash. Okay? I think legend is wrong on this point. The real reason it crashed was because they missed a minus sign out, but they didn't actually miss a minus sign out. What it was the pseudocode said x bar, meaning the average value of x, and the person who transcribed the code didn't realize the bar was significant and just used the actual value of x, didn't do the average of the time sequence. So that was a specification pseudocode error. But apparently this was not an uncommon mistake to make, and you know, this sort of thing did happen in real code. Anyway, so moving on, so history of programming in 07, okay? Those who cannot remember the past are condemned to repeat it. That's not quite how I remember the quote. I thought it was condemned to reinvent it or something, but this is apparently the actual quote, and it comes from some philosopher writing in 1905, or at least that's what it says in Wikipedia. So it's sourceable knowledge. I'm sure someone will correct it if it was wrong. Anyway, I've never heard of George Santayana. I don't know if anyone else has, but. So, oh, right, sorry, I didn't mean to put that slide up. Oh dear, I've spoiled the surprise. So I'm going to ask you what the first programming language was, and you'd have all said Fortran. And I said, no, you're wrong, it's not Fortran, it's a language called the Plan Calcul, which was invented by a German mathematician, whatever, I'm not quite sure what you call him. in the 19... Sorry?
Electrical engineer.
Electrical engineer, yes. I mean, quite extraordinary. He invented this programming language in 1945, apparently. So you can imagine post-war Germany was probably not the best place to be a computing pioneer. But it was truly remarkable. And his work didn't get published until 1972, and it didn't get implemented in 2000. But he had a programming language. He really had a programming language, and it was not like any programming language you've seen. Okay, so that's what it looked like. Had a kind of two-dimensional aspect to it. And I don't even pretend to understand this, but there's a paper that explains what it does. This is apparently a program that does syntax checking of Boolean expressions. So that in itself is interesting because he was doing abstract symbolic manipulation in the 1940s. It wasn't numerical calculations, it was actually abstract symbol manipulation. And he also wrote a program to do chess, or at least to check whether chess moves were legal. So it wasn't just numerical stuff. It was, as I understand it, the idea is that this is a sort of the VKS. The V is a variable, K is some kind of index, and S is a comment. But to be honest, the comments don't look very informative to me. Like I mentioned sigma. The two-dimensional structure of it is, I don't understand that bit at all. But if you're interested, I'll provide a reference to the original stuff. But there's now a kind of museum and a website dedicated to his work, and it's becoming better known. So I think that was a really remarkable thing, but nobody knew about it at the time. So sure enough, the first programming language was Fortran. The first one was actually used.
I think I ought to put in a plug there for Mercury autocodes.
Oh well, yeah. I'm not counting autocodes, right? We can argue about whether autocodes are. Yeah, this is what I'm talking about here. Okay, so in 1950 to 1955, before Fortran appeared, there was this idea of kind of these autocode things, and I don't know very much about them. When I was at Newcastle, my colleagues would talk wistfully of Atlas autocode, and I didn't know what they were talking about because it was just before my time. But they would talk about this Atlas autocode, and we could argue about whether it was a real programming language or not. But that sort of thing was a precursor to Fortran. I think the point about Fortran was it let people write down mathematical formulas in apparently some kind of English transcription that then you could execute on a computer. So it was a very sort of direct representation of what you're doing. So anyway, this was the kind of period when things were sort of bubbling along, and then by the end of the 60s, the first compilers for high-level languages were becoming available, and there was this kind of split between scientific computing and business computing. So you had Fortran, which was the numerical scientific stuff. You had COBOL, which was for business users. You had ALGOL, which was seen as a language for describing algorithms, and so the ALGOL didn't have any input-output statements in it. Okay? There was no standard, so you couldn't write a portable ALGOL program, but you could write a portable algorithm, and a lot of algorithms were published in ALGOL, but because people were just interested in the algorithm, the input-output bit was missing. You also had Lisp, and you had APL, and the premise of my talk is the battle lines were drawn at this point, and not a lot has changed since. Okay, now we could come back. Obviously, quite a lot has happened, but I would say that I would argue that the kind of fundamental things were kind of laid down at this point. And I think a lot of interesting things happened in the 60s, but this was where we were. So if we go to my poster, we can see this quite clearly, actually. So there's Fortran, and you can see COBOL, slightly independent, spinning off from some kind of Flowmatic autocode thingy. There's APL, which is sort of popped out of nowhere. There's ALGOL, which is kind of spawned from Fortran, and there's Lisp. And Snowball seems to have appeared in 1962 from now. I don't know much about Snowball except that it was a string manipulation language. So I guess it had things like regular expressions in it, but I don't know. But it was kind of a string stuff. But you can see that there are basically those 5 languages, and that's the start. And everything is kind of descended from those 5 things, and almost all of them are descended from ALGOL. well, that's my premise. We can argue about it. So, where are we? Go back to this. Right, so, Fortran. So there's Fortran. That's John Backus, who invented Fortran. And I've shown a bit of Fortran already. This is a program for printing cubes. And I've just kind of used this example for all of them, just to give you a very brief flavour of the language. Okay. This is COBOL. Well, that's not actually a program for printing cubes. It's just a different fragment of COBOL that I found somewhere. You can see COBOL is a very, very different style. It really is written out in English. I don't know, did everyone see the Grace Hopper Google Doodle that was done a couple of months ago? Did anyone see the comment that somebody wrote saying that Google got the COBOL the wrong way round? Because the idea was when you click the thing, it word and clicked, and it did a computation, and it worked out the age of the language. And so what it should have, and what it said was, let me get this right. It said subtract current year from birth year giving age. Which that kind of illustrates the trickiness of natural language. It sounds plausible, it's actually the wrong way around. It should be subtract birth year from current year giving age. So Google apparently got this wrong in their doodle, and then they had to fix it fairly quickly. So I don't know if that's true or not, but I was quite amused by it. And you can see how that happened. So that's COBOL. And anyone remember Dijkstra? Dijkstra was very outspoken about languages. So he said, the use of COBOL cripples the mind. Its teaching should therefore be regarded as a criminal offence. I'm pleased to say I've never taught anyone COBOL. I've never programmed, so you can't knock me out. And he said, Fortran, the infantile disorder, by now nearly 20 years old, and this was in 1968, is hopelessly inadequate for whatever computer application you have in mind today. It is now too clumsy, too risky, and too expensive to use. Okay, so that was Dijkstra in 1968. So, where are we today? I find this statistic absolutely unbelievable, but it might be true. Apparently, the Gartner Group reported that in the late 1990s, there were 80% of the computer code that existed was written in COBOL. Okay, so perhaps tells you something about the verbosity of COBOL if that's true. But 80%, so that's 240 billion lines of code out there written in COBOL. But the amazing thing is this second fact. More than half of all new mission-critical applications are still being created using COBOL. So they reckon that 5 billion new lines of COBOL are being written every year. I don't know who the people are who are writing this code. I mean, do any of you writing COBOL? No, do you know?
I was writing it in the 90s.
Okay, so right. You're one of the guys contributing
A lot of
to
other stuff.
this mound of COBOL.
We had a
Yeah.
specific
Yeah.
How many billion did you write?
I've never met a COBOL program.
I thought they were in care homes.
Back half of 1985.
Anyway, so I don't believe that's all I'm going to say about COBOL.
Well, it is true that a lot of code that is on IBM mainframes is still COBOL.
Absolutely.
Although a lot of new code is not COBOL.
Yeah.
But that accounted, certainly in that era, that accounted for a large proportion of the code, and probably still does.
This is late 1990s.
Yeah.
This is not
Yeah,
the
yeah.
70s or the 60s. It's
No, and it's true.
How much functionality did that deliver?
Yeah.
Because the signal to noise ratio was quite high.
Yeah.
Oh, no,
And as a result, if you've got COBOL skills, you can probably earn quite a lot of money.
Yeah.
In maintenance program.
Well, this is a serious issue, actually, these legacy systems written in languages that nobody knows anymore and never gets taught and so on. Anyway, yeah, so that's COBOL. Of course, I mean, nowadays we have object COBOL, as you'd expect, and structured pods. COBOL was always structured, but we have object COBOL now.
Were these important people in the change date in 2000?
Sorry?
When we changed over to 2000, there's lots of projects.
This is just, that's an interesting question. I mean, I have no idea. I mean, the Y2K problem might have been a natural end to COBOL, but rewriting
it was a
240.
reinvestment in COBOL, fixing those programs.
Right.
Yeah.
Okay. So they probably got.
No, seriously, there were figures reporting that 50% of all programming Spain was going into maintenance of pre-existing applications.
That's interesting. Yeah,
Up to that
so I can
point.
imagine that they'd actually revise those things. Anyway, okay, so much for Cannonball. What about Fortran? I think, I don't know if people would agree, but Fortran is essentially the language of choice for high-performance numerical computing. This is what people, all the nuclear physicists use. This is what weather forecasting uses, I believe. You know, this is what runs on the Cray supercomputers and so on. And
Machine tools.
yeah, Fortran it's essentially been tuned for scientific numerical stuff, and the supercomputers can run. It's very good support for data parallelism, so that's why. And there's this huge amount of sort of standard numerical libraries. The old NAG library. Anyone remember the NAG library? I'm not sure if that was Fortran or Algol, but it was Fortran, yeah. So that sort of thing is still around and being used, and so a lot of really intensive supercomputing tasks are really going on in Fortran. So it's still around. And in fact, when I started programming, it's so ubiquitous that there was a quote from somebody. I couldn't trace it, but the quote was, "I don't know what programming language people will be using in the year 2000, but I know it will be called Fortran." Okay, and I must have heard this quote around 1980. So does anyone know who said that? Well, I've not been able to trace it, but I asked a couple of colleagues at Newcastle, and they said, "Oh yeah, Brian said that was the kind of thing. Brian Ruggles thought that was the kind of thing that Alan Purvis might have said." I don't think it was him. I thought it was something like Don Knuth or Tony Hoare. But anyway, and sure enough, there is still Fortran around. And I actually was in a bookshop, and I picked up a Fortran book about Fortran 2000X or whatever it was, and I opened it up, and I thought, that's not Fortran. It was unrecognizable to me. Because the stuff I was programming, I was, before Fortran, I wasn't using Fortran 77. That's a Pinko computer science language. I was using Fortran 4, proper IBM Fortran 4, the old Fortran. And I think the point is, it might still be called Fortran, but it isn't really Fortran. It's morphed into something else. And this quote here, as I said to my comments to the committee, Fortran 90 would be a nice language. Too bad it's not Fortran. It's turned into something else. Anyway. Here's Algol. Algol, highly influential precursor to Pascal, Simulo, etc. And Tony Hoare's comment, Algol 60, a language so far ahead of its time that it was not only an improvement on its predecessors, but also on nearly all of its successors. And we'll come back to that later, because this is one of the interesting issues. But anyway, lots of interesting ideas in Algol 60. Lots of brackets, lots of irritating superfluous parentheses is what some people think this stands for. It's AI language based on the Lambda calculus, a bit esoteric perhaps. And nowadays, this is a program in Lisp, and this is how you would write it in Haskell. So you can see it's very different sort of much more natural way of expressing it. The columns is equivalent to the pattern matching in Haskell. So we've got if n equals 0 and nil, which is the empty list. Otherwise, append these two things. So cubed n minus 1 and append list of n followed by n cubed. Okay, so you can see that Haskell is a much easier kind of transliteration. Looking at my evolution table over here. I thought, well, where did Haskell come from? Okay, so Haskell is here, okay, and it came from Arando and KRC, and Sassel, which are languages that David Turner developed at Kent, and then it traces back to something called ISWIM, which is, I think, stands for I see what you mean, or something.
If you see what I mean.
If you see what I mean. That's what it is.
I said that. No, isn't it? If you see what I mean.
That's what it is, yeah.
It is definitely what it is, because that's what people, and they told me it was, and he invented the language.
He invented it, right. But it doesn't seem to have anything back to Lisp, and is that correct?
And there's a connection the other way, actually.
Yeah.
That is, McCarthy learned from Peter and didn't the back closures and put them into this.
Okay, that's interesting. There's also a link to ML as well, which is the name that kind of appears from nowhere. So maybe, anyway, I just think I don't want to get into I don't know very much about the history of functional languages, and this is a whole specialty in its own right. But anyway,
But there's a lot of Lisp derivatives which are actually making a resurgence now. I mean, there's
you're anticipating
closure, F sharp, Steam, and a lot of these are actually. I mean, I think it's the new. As you say, it's back history. It's the new thing because of the explosion of cloud computing.
Absolutely, yes, and that's part of my conclusions.
Even the fairly historic language now.
So APL. Now APL was one of the. So when I APL had its own distinctive character set, which was so distinctive that Python couldn't render it. So I ended up with all these black splodges. So I actually went to a lot of trouble to find out what the black splodges would be, and I went to even more trouble to type them into PowerPoint, which was very difficult because some of those characters just don't exist, just aren't in PowerPoint. So with great difficulty, that's what the program should be, okay? And really, I'm not sure that you can use whichever one you want. I'm not sure there's much difference, okay? So this is just completely weird. But apparently, I mean, somebody said IBM used to run the business using APL because it was basically a numeric. It was kind of manipulated arrays of numbers in this sort of array manipulation technology. So before you had spreadsheets, but you could do financial calculations in it, and you could express things very, very compactly.
So this still has a community of users and programmers.
There's still people out there using it.
Substantial.
Yeah.
Industrial.
Yes. Yeah. I read, according to Wikipedia, people are using it for financial trading, which is a bit surprising. But it, very interesting language based on a mathematical. It used so many weird. It didn't use quite as many weird characters as the Article 68 specification did, but it came close. And it had. IBM made special typewriters, special golf balls, which had the APL character set on, so that you could type this stuff. I won't try and explain what those programs do to you, but perhaps I'll show you what they look like in Haskell. Okay, so that's the. This you can see this is a combination of a map function. Where's the mapping going on? Okay, so iota n, for example, generates a list of 1 to n, which would now be done as a kind of set comprehension, and then map the cube. That's just kind of implicit. You don't need to say map. If you take a function and you apply it to a list, it just does the map automatically, I think. And then the rest of it is really about turning it into a nice list with 2, 3, 4, 5 down the side and 8, 64. 125, and this bit's formatting. That's the actual computation of the cubes, and the rest is formatting it nicely as a table. So, but that's what it is in Haskell, which is curious.
Robert, sorry, but what is your point? They are both. I'm sorry, I missed the point. But they are both higher order languages.
Yes, and well,
that the syntax of Haskell is more pleasing than APL.
Well, I'm really showing you 5 very different languages. Okay, but to try and explain 2 of the more esoteric ones, I'm relating them to Haskell for people who understand Haskell. And what you can see here is that APL is doing kind of higher order functions. These operators are sort of, you could understand them as higher order functions so the program idiom is a program idiom that would be familiar to a Haskell program, except it's been encoded using this strange APL notation. But it will be a familiar idiom now.
I see. Okay.
That's kind of what I'm saying. But this is more than a side that I'm not really talking about functional programming.
Excuse me, but I don't think there really are any higher order things in
APL. Okay,
it's like
yeah, there are fixed constants. They're constants.
Well, it's higher order. No,
you can't write higher order functions.
It's like when you've got the equivalence of map and fold. I mean, reduce is like fold. Is that the same?
Yeah. It's using the concept of map and fold. Yeah.
There's a constant. They're just constants.
Okay, when you can actually produce, you can construct the functions. Yeah.
Okay, gentlemen, I'm going to curtail the discussion. Yes, this is one for the wine bar.
So, anyway, Dijkstra liked APL in this. Okay, so he said APL is a mistake carried through to perfection. It is a language of the future for the programming techniques of the past. It creates a new generation of coding buttons. I think you like that. And he said, Lisp has been jokingly been called the most intelligent way to misuse a computer. I think that description is a great compliment because it transmits the full flavour of liberation. It has assisted a number of our most gifted fellow humans in thinking previously impossible thoughts. That's a very interesting comment, I think. And it kind of echoes with the I don't know if you know the story about Tony Hoare inventing quicksort and not knowing how to write quicksort down because he didn't understand recursion. It was only when somebody explained the concept of recursion to him that he was able to explain quicksort recursively.
Yeah. It was when he went to a class on Algol 60, which
yes,
at Sussex, and that. It was that enabled. It was the language rather than the concept.
Oh, it was the language.
He already knew about. He knew he wanted recursion, but he didn't know the language of it.
Oh, okay. So I missed.
He told me this the other week. So.
Okay. Straight from the horse's back. Anyway. Okay. And I think Lisp, one of the interesting things about one of the classic things in Lisp is there's no distinction between program and code. Okay. And so that and the interesting idea is that you kind of write a meta-circular interpreter. You can write a Lisp interpreter in Lisp, and it kind of reads Lisp programs and executes Lisp programs. It just treats them as data. And I think we're seeing a lot of that kind of idiom in current languages with these kind of generated technologies and things being used. So I think these ideas have been around for a very long time in Lisp, and I'll say more about this later. Anyway, okay, enough of that. So that was where we were in the 1960s. And, so only five languages, very different, and already lots of interesting ideas lurking there. So what happened next? Okay, so we had a whole spate of Algol-like languages came out. Algol 60, Simula, Algol W, Algol 68, and I'll talk more about that later. We had the birth of structured programming, the go-to statement considered harmful. That's a very interesting debate in its own right, but we'll leave that aside. Somebody had the temerity to write a paper 10 years after Dijkstra called go-to statement considered harmful. And he really got his head in his hands, actually. I mean, Dijkstra published a paper saying how disappointed he was by the level of understanding of computer science that was supposedly being shown, and he demonstrated how the guy basically described the problem that he said was most elegantly solved by go-to statements and blah blah blah. And Dijkstra pointed out that his solutions had various bugs in them, and he really, it was pretty humiliating. I wouldn't have liked to have been that guy. Anyway, so the interesting thing is what happened with Algol, what I'm going to call the Algol Wars, which kind of led to a split in the programming language community, and I'll come back to that. Because it's a very interesting bit of history. IBM tried to bring together these two different communities, this kind of the business and scientific world with PL1, which kind of ultimately, I think, failed, but a lot of interesting work was done on formal specification of languages. Cliff Jones was, I think that was all back around PL1. And as hopefully you all know, object-oriented programming was invented in Norway by Dahl and Nygaard from the Simula 67, and Stroud C++, claims direct ancestry, and Smalltalk claims direct ancestry back to Simula. So object-oriented programming was a very early idea, basically, they were actually, what they were thinking about a simulation, they were wanting to do a kind of simulation language. And along the way, they kind of accidentally invented object-oriented programming. That wasn't what they were trying to do, but they actually saw it as a sort of generalization of block structure. So it was just kind of the next step in the evolution of blocks and so on. So the basic idea was that you had a special kind of block that you could enter, and then you could leave the block prematurely, but the state of the block would remain. And this gave them a notion of a kind of active object. So they had sort of coroutines running these things. And so you kind of start up all these classes or objects in parallel, and they'd all do a bit of initialization and come back. So you'd have all these autonomous objects, but they'd be preserving their state. And I think they used a data structure called a cactus stack or something like that to do this instead of conventional heap. Well, they might have done. I'm not sure about that. But there's a story that Alan Kay figured out was basically given this similar compiler to debug. And he stretched out the listing down the corridor and crawled all over it and said, somebody said, this is an Algol compiler, but there's something funny about its stat discipline. I don't understand it. Can you see if you can figure it out and debug it? So Alan Kay crawled all over this thing, and literally, and had the insight and figured out what was going on, and that was how I came to understand the idea of objects and so on. Anyway, in some sense, the point is that a class is like a block, but it contains declarations and code, but it continues to exist after the code has been executed. This is how they thought of it. So you sort of enter these blocks, and you get left behind with the reference of it to it. So just to show you, thought I'd show you some similar. So that would have probably been valid similar mid-60s. I think mid-60s. Now, if we change all those begin ends to curly brackets, and if we change the procedures to voids and we swapped around the integers a bit, there is no difference between that. There's only one significant difference between that and C++ class written, say, 25 years later. So what's the difference? Can anyone see what's not there that C++ has?
Access.
Exactly, public-private. Okay, very interesting. They invented the whole abstraction, they invented dynamic binding, but they didn't think encapsulation was important for some reason. So the only thing that Simula didn't have was the notion of public and private. And I don't know why that was.
Because real programmers.
They were real programmers. Maybe that's right. They were real programmers. But anyway, so 20 years of progress, with changing begin to curly brackets and adding public and private. Okay, so that's not bad. Did anyone hear Barbara Liskow's talk a while back? So Barbara Liskow, very good talk actually. She talked about how she invented abstract data types. It was one of the things I think she said, which I really struck a chord with me, was how when she got into this field, when she was, I think, looking back, she'd gone back and read some of the classic papers that were published around the time, and she thought how many insights, how good and worthwhile they were even now. The insights in the papers that were published were still just as valid sort of 20 years on. And I think, I was fortunate in that when I did my master's in computer science, I did a course on what was called programming methodology, where I was given some of the classic papers on modularity and structured programming to read, and we did this as a kind of seminar thing. I'm sure people get taught that way anymore, but it's really useful to get back to this stuff. But Barbara Liskow, she said, oh, well, we were kind of vaguely aware they were doing something over in Norway, but it was a long way away, and we didn't really know what they were up to, And there was definitely European-American split, I think, because all the Algol stuff seems to be predominantly European, I think. Anyway, then we had Pascal, and I forgot. Yes, I brought along some books to show you. So I'm sure you'll recognise some of these. These are all first editions, or the first languages. Actually, that's a second edition.
They look old.
So that's C first edition. That's Stroud first edition. That's Pascal. Just Modular 2 second edition, I'm afraid, but it's, Now, does anyone notice anything about these books?
Yeah, they're old.
Well, they're old. They're thin. They're thin.
Yeah.
Right? That's very interesting. They're thin. And in fact, all of these books are both a textbook on the language and a specification of the programming language. So the actual specification, even C++, the specification, the reference manual, the specification is about, it is literally that much of the book. Okay, the rest is the textbook. That's the language specification.
Well, that's the syntax.
Yeah, well, the syntax, and I think some semantics is in there as well. No, I'd say there's some semantics in there. Yeah, I think it's semantics. I would say. And the same with these as well. And then this book is just a classic. So if anyone's interested in this, have a look at it afterwards. So anyway, 1970 to 80, we had, I did about abstract data types, but object-oriented programming wasn't really. It was all kind of abstract data types and structured programming and modularity. It wasn't really objects and classes and things. Even though they'd been invented by Simula in the 60s, they were kind of forgotten about here. Unix and C, of course, and Xerox PARC. So Smalltalk and Mesa were kind of bubbling away in the background. So Mesa was a interesting system programming language with all sorts of support for compilation of large modules and so on. And Smalltalk, of course, went through several versions before it emerged as Smalltalk 80. Okay, so moving on.
Can I just butt in with that? I think you've glossed over the origin of C there.
Yes,
which
yes.
Can be traced back to alcohol.
Yes, yes, it can. In fact, let's have a look at my my thingy and see where C comes from according to this.
BCPL?
Yeah. So C, yeah. Okay.
BCPL.
So as we know, C. There's C. Move it up a bit. C comes from B, which comes from BCPL, which comes from CPL. So CPL, I think, was called Common Computer Programming Language. Combined Programming Language.
Sorry for combined Cambridge and the University of London.
Right. And BCPL was Basic Combined. But was it Basic?
Well, actually, it's a different language.
It was completely different. Yeah. But BCPL was essentially a typeless language, because I did programming, it was typeless. So you let you manipulate integers and words and pointers and things without. So C actually added a type system. And people are quite rude about C. They see C as just a high-level assembly language. Actually, I think it's a typed.
It certainly wasn't for the first 4 or 5 years.
Yeah,
the first 5 years of its existence. The typing was brought in by Bjorn Stroud.
No. I think it had the types. I mean,
it had data types, but there was no.
It didn't have classes. No, clearly it didn't have classes.
No, it didn't have any type checking.
It did. Yes. It did. It definitely did. Yeah. I think it. Anyway,
we should continue.
We were talking about that.
We should continue.
But CPL, according to this, it was spun off Algol 60. So I think these Algol, C in some sense is an Algol-like language, and that the only real difference is it uses curly brackets rather than begin end. Actually, there's actually two interesting differences. I might, since you brought it up, I might skip to some. I think that there seems to, as far as I can see, there's two schools of thought on programming languages, syntax, roughly. Well, there's more than two, of course, but let me see if I can find the right slide. Okay, so we have Pascal-like languages. So Pascal-like languages use begin-end, they use colon equals for assignment, they use var colon type for declarations, they use procedure from type to declare functions and procedures. Sometimes they put function there, sometimes they don't. They let arrays have arbitrary dimensions, they let procedure declarations be nested. That's the significant difference, that C doesn't have that. Local functions essentially, functions declared within functions. And examples of that will be Pascal, Module 2, Ada, Oberon, Object Pascal, Delphi, that school of languages. And then the other school of thought, C-like languages, they use curly brackets, they use equals with assignment, they write the type declarations the other way around, they always index arrays from 0, they don't have nested methods and functions, and that's C, C++, Java, C#, all of those languages. So I don't know quite where that split came from, but I think it was a sort of European US split. Certainly a European East Coast US split, because East Coast Bell Labs, somehow that's where that came from. Because the West Coast America, the Mesa, the stuff going on at PARC, they were using the modular style of syntax. Anyway, that's just a sort of an aside. I think it
was because it's all out the type error and program on very slow other types.
Yeah, so maybe they
type more characters than that.
Yeah, so maybe that's what was going on. Anyway, so okay, so moving on. So by 1980, Pascal was widely adopted as an introductory language for teaching programming. And I remember having an argument with someone about this, and they were saying what a wonderful language Pascal was, and I was saying, oh, poo-poo, I'm a Fortran programmer, I don't believe in these Pico computer science languages, I can do anything I like in Fortran, why do I need Pascal for these things? I knew perfectly well that it wasn't serious, but it was, so certainly during the 80s, Pascal and in some cases modular, that this was the classic language. Unix and C became very widely known, Ada came out. Then Byte magazine published a special edition devoted to object-oriented programming and Smalltalk 80. Okay, does anyone remember that? It had the coloured balloon on the front cover. I've probably still got a copy of that somewhere. And that was the thing that brought object-oriented programming to the world in the guise of Smalltalk. And unfortunately caused a lot of confusion by going on about message passing rather than dynamic binding and so on. So, but that's when it happened. And C++, which started life as C+ classes, so it was very much influenced by Similar, started to become popular as an object-oriented extension to C. And in the early 80s, I'm not sure when, 82, 83, let's have a look. Actually, on my chart thing. We had this peculiar language, and I remember this language coming out. So let's see with classes, which is April 1980, and it became C++. And there's this language here called Objective-C, which is a kind of bastard offspring of C and Smalltalk. It was invented by a guy called Brad Cox, who was interested in the idea of software as reusable, integrated components sort of thing. So he was trying to have this idea of a kind of software factory where you had software IC. So in the same way you can buy integrated components from a catalog, you can buy software components from a catalog. And he had this language called Objective-C, and it was this bastard mixture of C and Smalltalk. So basically you had C, and then every now and then you put some square brackets and you embed some Smalltalk in it. And I thought, that's a stupid idea. That'll never last, I thought. And guess what? That's the language that Apple used for programming iPhones. So somehow that language has survived for 30 years and is now probably very much in demand. People who can program in that language are probably more accurately program in the frameworks and the libraries that Apple have underpinning that. But for some reason, Apple really liked that language. They found it gave them what they wanted, and so they supported it and pushed it and developed it. So I think the GNU C compiler will compile C, C++ and Objective-C, and I suspect that's because Apple pushed the money into the GNU Foundation to encourage you to develop it. Anyway, that's just an aside. But
it's not actually Smalltalk that's embedded. It's a message passing in Objective-C.
It's a sort of Smalltalk-like syntax, is what I mean. It's not literally Smalltalk. Yeah,
it's a C syntax with the semantics of Smalltalk.
Something like that. Well, it's become...
because they thought they wanted something that was more readable than Smalltalk.
It's actually an interesting... I was thinking about this last night. It's actually an interesting example of what is the breadth... why do languages survive? And they survive by kind of evolving and morphing. And perhaps this is why this thing worked. Because switching from C to Smalltalk would have been too radical. But grafting a bit of Smalltalk-like stuff into C made it possible to create a language that was kind of familiar to people, but they could gradually put the Smalltalky stuff in and then use more and more of it.
I don't think that's an accurate description to say grafting Smalltalk into C. It's a C syntax applied to Smalltalk.
Okay, right. I think it's changed a lot over the years, but okay, maybe I am misrepresenting what it is. Yeah.
Just to say, when you skip past Ada, the remarkable thing was that the European competitor won. And it was basically Anglo-French, wasn't it?
Yeah, it was. Yes,
the offering that actually won the competition.
Yes.
It was pretty surprising.
Yes, it was. Though, that's yes. I mean, I could give a whole talk about the modular languages. That's a different talk. I did see an interesting quote actually in the paper about Algol 68. And in fact, I've probably got it here somewhere. Yeah, let me just show you this. Let me see if I can find it. Right at the end, I think. There we are. I can't read it. In 1974, I was stopped in the corridor by Jean Ishbert, the author of the language list and the designer of what was to become Ada, on his way to the success of multi-religion dollar. He said to me with great emphasis, "We're going to do right what Algol 68 did wrong." Have they really, I wonder? But that's just an interesting link with what you were saying, you know. Anyway, we could come back to Algol 68. It's an interesting thing. But, right, okay. So, you say this is still the introduction, you know.
I think we're better crack on.
Yeah, indeed. So the 1990s, I think we had, you know, C++ became widely criticized for its complexity and so on. Java emerged as a kind of safe alternative to C++. We got this kind of growing interest in dynamic type languages, you know, partly driven by the web, I think. We also, I think the component-based ideas, you know, came to fruition, particularly with Microsoft's COM technology, which really is remarkable. You know, I think that the ability to sort of drag and drop and reuse components is very powerful. So that was the sort of 1990s. Also, I'm going backwards. And then 2000. I mean, there's a whole separate discussion about Microsoft and Java. Okay, so in 2000, I think, having tried to subvert Java for their own purposes, Microsoft, and being slapped down by some, and that was actually an argument about how to do event handling, and so Microsoft proposed some extensions to Java that would make it more friendly for Windows programming. These easy extensions were called delegates. And Sun said, "Oh no, you don't need delegates. You can do all this with anonymous in the classes. You know, you don't need these fancy delegate things." And so there's a white paper that Sun wrote saying why you didn't need delegates, why you didn't need closures and lambda expressions, and why you could do it all with classes. And there's another white paper that Microsoft wrote, which was called "The Truth About Delegates," which is, you know. And so somehow what was a basically commercial argument became an argument between the language experts who were kind of coming up with all these sort of language arguments to kind of justify the commercial position. But Microsoft were basically forced to abandon Java, and so at one point they had a language called Visual J++ or something, and then they eventually gave up and they produced their language called C#, which is basically Java but with all the keywords spelled a different way, so that, you know. Anyway, but that developed, I think, an interesting synergy between Java and C#, because C# got a bit ahead of Java, so Java took some features from C# and they kind of just juggling a bit. Then we got really sophisticated programming environments that were really using the power of the, you know, building kind of abstract syntax trees and parsing the languages and then doing all kinds of helpful things. If anyone's used IntelliJ, you'll know exactly what I mean. You know, they're putting the pleasure back into programming or something. Programming with pleasure, that's there. And it's just amazing what that tool can do. I remember people talking about this kind of thing back in the 1980s, but I think it became a reality with these Java type things. Dynamic type languages increasingly popular, particularly for web development, and I couldn't resist. Everyone wants closures, you know. They either had them or they wanted them, or they were inventing languages that either them and so on. And, you know, this was where I could have done a 2005 to 2015, and I didn't. So this is where I'm stopping. But I think it was more or less more of the same. I think probably the most significant thing that's happened in the last 10 years is the growth of JavaScript as a JavaScript being taken seriously as a language. And again, we have a similar situation. Google has proposed a new version of JavaScript, and Microsoft said, "Oh no, we don't need a new version of JavaScript." And now Microsoft have proposed a new version of JavaScript, but it's different from Google's new version of JavaScript, so that's okay. So there's all of this sort of jockeying for position going on around the dynamically typed languages. But what's actually happening is interesting, because people are taking the statically typed languages like Java and C# and trying to put dynamic typing features in them, and at the same time they're taking the dynamically typed languages and saying, "We wish there was some static typing in these languages, let's see what we can do." So they're kind of coming at each other from opposite directions. Okay, so, right. So that's kind of where I think we are. So, don't worry, I'm not going to talk for another 10 hours. So there's all kinds of technical issues that came up during this, and I found an interesting quote from Tony Hall in the paper that he wrote on programming language design, and he said, "The language designer should be familiar with many alternative features designed by others and should have excellent judgment in choosing the best and rejecting any that are mutually inconsistent." And he made the observation that language designers should focus on designing features rather than languages. What he said was, "I have never designed a programming language, but I've designed programming language features. Apart from inventing quicksort and CSP and all sorts of other lots of other things, Occam, Tony Hall actually invented the idea of a record. I didn't know he'd done that, but the idea of the record, the structure, was Tony Hall's invention apparently. And that's an idea that's kind of lasted. Anyway, so I sort of made a list of all the things I thought I could talk about, and I think you could spend a whole, could give a whole talk about any one of those things and how ideas about that have changed over the course of this period. And there's lots of debates, and some of these there's been a convergence, I think. So exception handling, for example, I think there's more or less acceptance of the termination model rather than the resumption model. Multiple inheritance, I think, is more or less deprecated, but there's lots of arguments about it. People have recognised that what you need is inheritance of specification versus inheritance of implementation. They've made that distinction. So there's lots of sort of interesting issues here. There's this whole event handling, delegates, and closures, and anonymous classes type argument that went on between Microsoft and Sun, and is still going on. There's some really interesting stuff happening around here, which is kind of where my research interest was when I was an academic. I actually gave a talk to this forum a few years ago about aspect-oriented programming in Java, and using it as a way of enforcing security policies. And I think a lot of these things are about getting the right kind of expressive power in the language, and also getting the language to, in some sense, being self-contained and complete and extensible in a nice, elegant way. Okay, and I think that the trend towards domain-specific languages is part of that. So anyway, I could talk for ages about any of those. So I'm actually going to spend a bit of time talking about two things: closures, and then I'm going to talk about Algol, the Algol wars. Okay, so closures. Lambda the Ultimate. Okay, it was a series of papers that Guy Steele and Jerry Sussman published in the 1970s. And rather than giving you a long, boring talk about closures, I thought I'd just show you I'd give you a quick history of closures. I found a very nice website called A Brief, Incomplete, and Mostly Wrong History of Programming Languages. And I thought it had a nice summary of the sort of key points. So, 1936, Alan Turing invented every programming language that you'd ever need, but got shanghaied by British intelligence before we had a chance to patent them all. So, 1936, Alonzo Church also invented every language that ever would be, but did it better, producing lambda calculus, but which unfortunately was ignored because it was insufficiently C-like. Okay, so moving on. 1958, John McCarthy, Paul Graham invented Lisp, but it never caught on because there was a shortage of brackets. So it's really only influential in this area of key algorithmic techniques such as recursion and condescension. So, and then in 1970, Guy Steele and Jerry Sussman created Scheme, which led to this whole series of Lambda the Ultimate papers. Scheme was basically a lexically scoped version of Java. Lambdas are relegated to relatively obscurity until Java makes them popular by not having them. So if you don't know what all that's about, and what the jokes are, then I suggest you read this book. Okay, this is a wonderful book. If you've not read it, it will just change the way you think about programs. Okay, it's essentially the course that they use to teach engineering students about computing at MIT for a long time. They don't do it anymore. It's been changed, and there was a lot of controversy when they changed it. They've gone towards a much more playing with robots, exploratory type thing. But this was very much about they just started showing people Lisp, well, Scheme actually, and they just started writing down mathematical functions, and each chapter of this book is about a different kind of abstraction. And the first chapter is essentially about functional abstraction. The second chapter is about state I think it's about encapsulation of state abstraction, then it becomes object abstraction, then it becomes language abstraction, actually it becomes machine abstraction. It's incredibly deep, powerful book. Really recommend it. It's all free. You can download it from the book, from the web, and read it. And if you don't understand why classes and closures and blocks are all kind of the same thing, then read chapter 3 of the book, and I'll show it to you afterwards if you like, and just convince you that you can just write. You can write classes using closures and lambda expressions and things. You don't need anything else. So that was what they meant when they said lambda was the ultimate everything. You know, all you need is lambda expressions and lexical scoping and so on. Anyway, so let's look at Algol. Does anyone remember call by name in Algol? Anyone remember Jensen's device?
Yes.
Yeah, well, you see, so Algol had closures. They were called thunks, okay? And the idea was that if you had an expression that you passed as an argument to a procedure, when you evaluate, you didn't evaluate the function once when you passed it. You actually evaluated it every time you used it, and you evaluated it in the scope of the call. So if it referenced other variables, it would, and those variables had changed in the meantime, it would re-evaluate them. And this allowed us, and it was basically macro expansion. So it was, but it was done with a kind of hidden subroutine that was kind of called a very weird thing. But it led to this technique called Jensen's device. And the idea was that if you've got something like that, you've got some mathematical expression like that, you can write a summation function where you just essentially transcribe the mathematics into the call. And you just say, sum this expression over x from 1 to 10. Okay? And that would just work. Okay. Now you try and do that in Pascal or Java or something, it just wouldn't work. Okay. The reason it works is because basically inside the function you have this variable I, which is used in the expression. You use I as the variable to step over the thing, and every time you evaluate this expression, it re-evaluates it with a new value of I. So it's as if you've passed. What you've actually done is you've passed a lambda. You've passed a lambda expression in, but you're not needing to call it explicitly because you're relying on the fact it has this. It's a lambda. It has this free variable in it, which you happen to be using as your for loop. So every time you'd have to write it with an explicit call to the function. So it was perhaps an accident. They maybe didn't mean to invent it, but it was there. So that was back in Algol 60.
I was going to say at some stage, I actually didn't know about Jensen's device, but it seemed intuitive to me.
Yes.
And before I'd heard of it, I actually wrote a graph plotting program, which was to calculate the impedance of an electrical circuit at different frequencies and the phase change, which gives you all you need to know. Yeah. You can write down an expression for the impedance, which is frequency dependent, and then you just run it across, frequency, and it comes up. Well, as a side effect, you print the points on the graph.
Yeah, exactly.
Yeah. And I didn't know. Yeah, so it was really intuitive.
That's exactly the point. It was intuitive, and it made sense to mathematicians and physicists at the time, and they didn't really realise there was anything funny about it. It just worked.
I'm not sure, some people claim it was an accident so that they use call by name rather than call by reference, but I'm not sure that's the case because it's really just normal order evaluation of the language expressions.
It's essentially substitution, and it's certainly not called by reference, and it's not called by value or anything. You evaluate the argument every time it's used, and you evaluate it in its lexical scope. So if it uses parameters that were defined in another scope, you evaluate it with those, and so that's why it works. It's a fact. It works because you have an expression over x, and you've passed in x, and you're modifying x, and therefore you're modifying the expression. If you didn't pass in x as an argument, it wouldn't really work because x would never change.
No, but that's precisely beta reduction of language.
Yeah, I suppose it. Well, okay, I'll take your word for it. Anyway, it's really interesting. But what I was reading about this, and somebody said it was macro expansion, and that was very natural to people at the time because they were used to assembly language. I think it'd be very alien to a Java program, this kind of thing. They'd probably be quite comfortable with the idea of passing in an object with a compute function, you know, some kind of thing that represented a function, and then passing all the values between 1 and 10 to that function and evaluating the function explicitly. But the point was, this is done implicitly, you know. So it's an interesting thing. Anyway, so what about Java? Well, we're still waiting. Real soon now, we hear. Java 8 is expected in March 2014 and will finally include language support for Lambda expressions. You know, and they've been arguing about this for about 10 years, I think. But maybe not as quite as long as that, but it's been a long argument. And I think the value of them has been recognised, but there's been various proposals that have been debated. There's a fascinating sort of history of this, lots of all the arguments for and against the different proposals. There were at least 3 different proposals, but for how to do this in the most, and of course they were worrying about feature interaction and syntax and so on and so forth. So it's not easy to add a new feature to an existing language with a huge amount of code in it, particularly when you have concerns about efficiency and things like that. And in fact, you might be familiar with the sort of restriction in Java about anonymous inner classes. They're allowed to reference lexically enclosed variables, but only if they're final. You can't reference a variable because that makes it difficult. So it's a rather strange restriction, but it gets them off the hook. But apparently, this was a conscious decision they made, not for efficiency reasons, but because they thought their users wouldn't like it. They could have relaxed that restriction early in the days of Java, back in Java 1.2 or something when they introduced this. But their users thought, no, we don't want that. That would have a hidden cost. We don't want that. We want to keep it the way it is. So they lost a bit of expressive power there, and that's interesting. And it's echoed by something I'll come on to in a second. So, Algol wars, okay? Remember what Tony Hoare said, Algol 60 was an improvement on almost all of its successors, okay? So where did that come from? Well, basically, there's a big bust-up. There was this group, which was IFIC-WG 2.1, which was called the Algol Committee. And Algol was seen as a significant language, and everyone was very happy with it. They were going to design the next version of Algol. So what was the next version of Algol going to be? And at one point there was, Algol X and Algol Y. There were various different proposals. And what Tony Hoare said in his during the awarded speech was, the language they came up with, he described with Algol 68. He said, he was absolutely astonished when the Algol working group, which consisted of all the best-known international experts of programming language, basically apparently threw away a draft of Algol X and decided to adopt Algol Y, which was Algol 68. Okay, which is a line with such an unattractive bait, Algol 68. The best we could do was send in a minority report stating our considered view that as a tool for the reliable creation of sophisticated programs, Algol 68 was a failure. Okay.
Now, the main thing about Algol 68 was its definition, which was a very much
next couple of slides. Getting there. So here's the introduction to the minority report. Okay. We regard the current report on Algol 68 as a fruit of an effort to apply methodology for language definition to existing, trying out a new way of defining languages and a defining new language. We regard this effort as an experiment, and professional honesty compels us to state that in our considered opinion, we judge the experiment to be a failure in both respects. And look at the names of the people who signed this. Dijkstra, Bohr, Tursky, and Brian Randall, who I know very well from Newcastle. He wrote one of the first Algol compilers, the Whetstone compiler. And by this, and Tony Hoare, Niklaus Veert had already resigned in disgust and gone off and written Algol W and Pascal, and so he'd given up on this, and Peter Lau had given up on it. It was a real bust up, and actually led to the formation of 2.3, which was the Programming Methodology Committee. Here's a contrary view, which is actually a very interesting paper, which I found. Okay, This is by one of the authors, and he said, well, but this stuff, it was written tongue-in-cheek, it was meant to be fun. He said, look, here's an example of the syntax. How could you read that stuff without having a smile on your face, Well, so I had, referty, rosity, rosity, non-row slice. Referty rows, rosity, non-row primary subsymbol rows, leaving rosity index a bus symbol. I don't think the humour translates somehow. I mean, maybe I haven't got the right accent for it, but I think that's got something to do with the array subscript expressions, but I have no idea. I think it's about taking slices out of arrays. And it was a really weird thing. It was a two-level grammar. I think the idea was to try and capture the semantics in the grammar. So, you had a kind of grammar from a grammar. And I don't, as far as I know, it's never been used by anyone else, but it was something that was invented by Van Weingarten. And so a lot of it was about this weird notation. But the other interesting thing, but there were actually some interesting things in Argol 68. So, remember what I was saying about efficiency and referencing lexical verbs and things in Java. So concerns about efficiency. So apparently one of the things he talked about in Argol 68 was procedures delivering procedures, making procedures into first-class values in the language. And unfortunately this causes scope problems, but the difficulty is you can't enforce those you can't enforce the scope rules within their type system. So why have the restriction? Why not just let it work anyway? And they had a debate about this, but they were worried about efficient implementation. So they could have had closures, but they could execute scope closures, but they decided not to. But the only thing that prevents you from having them is a line in the language manual that says you shouldn't do this. It's not something that can be enforced by the compiler, you see. Apparently. They have higher order functions, but they nearly had coding, but they sort of stepped back from it. So they had a lot of interesting ideas in there. And I don't know if anyone knows about Argol 68 and the work that was Argol 68R, the work that was done at Malvern. So the first Argol 68 implementation done at Malvern, World Signals and Radar Establishment, part of the MOD. The very first Argol 68 implementation conference, they demonstrated a working Argol 68 compiler. And they subsequently went on to relax this lexical scoping restriction, and they implemented a form of object-based capability architecture, so they were doing object-based programming in Argol 68 using closures on a microcoded capability machine. And I don't know if this is true or not, but I saw a reference to say they weren't interested in native because they already had all the type security for their kind of defense military type applications in Argol 68 and their special capability machines. They also went on to invent a kind of strange thing they called it 1015 because at the time they had to give it a name, they looked at the clock and it was 1015, so they said, we'll call it 1015. It was a kind of algebraic abstract machine specification which was used as the basis of something called ANDEF, which was an architectural neutral distribution format that was standardized by OSF, and I think probably the CLR.NET uses similar technology. So again, these ideas go back. Anyway, Argol 68. So back to the future. So I came across this blog article while I was preparing this talk, and I just loved it because this is what my talk's about. So Google have announced an Algol-like language called Go. This was in 2009. And somebody thought it would be interesting to compare this language against an old Algol-like language, which he called GroundX. And he goes through pages and pages of detailed comparison of this feature versus that feature. And at the end, he decides that basically he thinks GroundX is better. So GroundX feels complete in a way that Go doesn't. Go might have way more in the way of features, but GroundX is more consistent in its features. In other words, the features are chosen to work together more orthogonally and consistently. GroundX is Argol 68. Very interesting. So, what does the future hold? I thought I put in a full quote from Ecclesiastes. What has been will be again, what has been done will be done again, there is nothing new under the sun. Who's a real pessimist? Yeah.
Sorry to jump back over a chapter break, but what happened to Go?
I think it's still out there. It's as far as I know. I mean, I've not looked in any detail. I believe it's a kind of I think it's Rob Pike is one of the people behind it. Rob Pike's a bit kind of anti-C++. So it's basically, it will be one of these languages that does object-oriented programming without using classes. It does it with record extensions, So it's the same idea as Oberon, and so I think it's that flavor of language. So it's a C-like, algo-like language, but it doesn't have classes, but it has all the kind of type extension, dynamic binding, records containing procedures and polymorphic typing. It has all those features, but it just doesn't call them classes. I might be wrong about that. I've not looked in detail. I think it's supposed to be used for cloud computing. Does anybody know any more about Go?
Google is still pushing it.
Google, oh yeah, Google are pushing.
I read an article by the head of the project that did Go, and he was also the head of Android, and he's saying, these are my babies. These are equivalent projects. It's as big as Android. Yeah.
No. It's a serious language, and Rob Pike's an interesting guy, but he's a bit of a, what's the word? A bit of a maverick. But he likes to be an independent thinker, do things his own way. Okay, so I think he I think he would be. So it wouldn't surprise me at all if it didn't have classes. It'll be recognisably object-oriented, or at least object-based, but it won't have classes because it will do it in a different way. I don't know in what sense it's cloud-based. I have no idea. But another interesting language, Pike did when he was at Google, is called Sawzall. Has anyone heard of Sawzall? So the Sawzall is basically a declarative way of doing MapReduce. Okay, but very, very elegant idea, so it's worth looking up. There's stuff talking about that. Anyway, okay. So, what does the future hold? More language awards. This is from the briefing complete and mostly wrong history of programming languages. 1996, James Gauntlet invents Java, which has all these features, and Sun Monkey has its novelty. 2001, Anders his work, or whatever, I apologize, I have no idea how you pronounce his name. C#, which also has all these features, and is also a novel language. Same thing happening with the JavaScript languages that Google and Microsoft are proposing at the moment, and arguments going on. So we're going to have language wars. Have you seen this? This is Kai Horstman's March of Progress. I love this. There's actually quite a lot of depth in here. Because it took a long time before you could do that in Java in a type-safe way. Okay? But to be able to do that in Java type-safely, you had to add autoboxing and you had to provide some kind of variant argument syntax. Okay? And then you can write printf in Java. But if you don't have that, you have to do that kind of thing. And Pascal has the same problem. The Pascal write statement was basically a macro that was expanded by the compiler, but you couldn't do the same thing in Pascal. You had to write it out longhand. And so getting the language to the point where you don't have to write it out longhand is what I mean by the syntactic simplicity, expressivity, and so on. Anyway, and this is fascinating. I mean, do people know how this works? I mean, it is brilliant. That's a function. So, and that's a code function. It's very interesting what's going on there to make it work. Okay, so some observations. I think programming languages succeed or fail for both technical and non-technical reasons. And clearly there's a lot of politics and personalities around what happened with Algol 68. But I think good language features tend to survive or get reinvented regardless. Okay. I think the first approximation, most programming languages end up with more or less the same features eventually. Okay, we are getting this convergence. Fortran doesn't look like Fortran anymore. COBOL is allegedly object-oriented. Everything is getting the same sorts of features. But I think there is this big problem about how you evolve a language with an established user base without breaking backwards compatibility, and particularly without breaking binary compatibility, which is something that Java, some are very concerned about with Java. People criticize Java's implementation of generic types for not providing explicit type parameters, for not making the type information available at runtime, but that was a deliberate decision. They use this technical type erasure where they throw away the types. But that's because it would break backwards compatibility if they did it a different way. So they did think about this stuff very carefully. And as Tony Hall said, this idea of language designers should learn from each other's mistakes and try to find a combination of features that work well together. Another quote from the unreliable history of programming, JavaScript was a collection of all the mistakes that there's ever been made or put together in a language. Okay, so, and there actually is a book called JavaScript: The Good Bits and the Bad Bits. And it tells you what the good bits are and tells you how to avoid the bad bits. So current trends and predictions. I think we're getting broad agreement and convergence from a common set of desirable language features, which include things like dynamic typing. I think probably a bit of type inference. Functional paradigms like closures and lambda expressions and things. I think we're seeing, increased use of syntactic sugar for expressive power. With things like the for each type iterators and so on. I think annotations are one of the most interesting ideas I've seen in recent years. Which is a way of extending the language by just kind of a very simple syntax that is you can do arbitrary things with, essentially by decorating things in the language. You can then write tools or libraries or whatever that pick up on those decorations and do interesting things. I think we're getting all this language-aware, refactoring programming environment type stuff. Clearly, Java and C star, where star equals, aren't going to go away. But I don't think Fortran and COBOL are going to go away either. I mean, for these legacy reasons. So that's kind of where I think we are. Here are some sort of key contributions. I think Fortran was the first optimizing compiler. Lisp, the whole symbolic computation thing. Algol, block structure, recursion, procedures, and object-oriented programming. Pascal, structured data types. Arguably that was done first in Algol W, but it was done better in Pascal, and this book really explains it. And the file type in Pascal is fascinating. It's a sequence of objects, and it's a recursive sequence of objects. You can have files of files in Pascal, so you can do really quite interesting things. I don't know how many compilers actually support that, how many runtime systems actually supported that, but it's really quite interesting. C system programming is mortal go. Mesa separate compilation, I think, and Algol 68. I thought I better add that. I think orthogonality. They really pushed orthogonality as far as they could, and you could say that Algol 68 is a kind of the apotheosis of the kind of procedural type language. I think it took things as far as it could. It's one way again. Here's a closing thought, okay, from John Backus. John Backus says that he thinks conventional languages are for the birds. They're all really low level. They're just extensions of the von Neumann paradigm. They keep our noses pressed in the dirt of dealing with individual words and computing addresses and doing all kinds of silly things like that, things that we picked up from programming languages. For computers. We built them into Fortran, we built them into PL1, we built them into almost every language. The only languages that broke free from that are Lisp and APL. And in my opinion, they haven't gone far enough. So that was John Backus back in 1981, by which time we had all of the languages pretty much that we know. And he said, they're all rubbish. You really got to get away from this kind of procedural type stuff. Okay? So that's the end. Thank you for your comments and corrections and amplifications. That's been very interesting. I hope you enjoyed this anyway.
I think we really have to thank Robert for a very, very detailed and thoughtful talk, which is a complete education on programming languages in itself. I think we've got time for 2 or 3 questions. I'm sure a lot of people are itching to get away. So let's start at the back then.
Can I raise one issue, which I think all current programming languages are virtually ignored, or they should have done, and that's static analysis.
Well, okay.
I think programming languages, in other words, should be more than just a compiler, which is typically what they are. And then after it compiles, you're on your own, so to speak.
Okay,
We need more facilities to aid the programmer to get something that's even approximately right.
I said right. Okay, so that's right. Okay, I kind of only partly agree with you. Well, I mean, I agree with your premise. Okay, that languages are more than compilers. I'm not sure I agree about lack of static analysis. I think there are. I think this is one of the things that's coming in with the annotations, and it's one of the things that's coming in with the automated programming support and so on. So for example, if you're writing if you're writing Java in a modern Java programming environment, the tool in the background will be pointing out things you're doing that don't look right, that you might like to think about. It will be suggesting better ways of writing your code. It will be pointing out potential bugs. And it's doing that because it has a lot of knowledge about the semantics of Java, and it's doing some kind of static analysis behind the scenes. I think, you know, there's a whole story, you know, there's a lot more to language implementation than just compilation. Okay? I think there's a whole lot of stuff that has to happen at link time and at load time and even at run time to make sure everything is correct and consistent, particularly when you worry about independent compilation and versions of things evolving and so on. So I think there's a whole bunch of issues around that. The Java class loader and the kind of checks that are built into the Java runtime in order to validate Java effectively does a static analysis of the class code to make sure that there aren't going to be any type errors in the code when it runs. So when Java loads a compiled class file, it actually analyzes it and does a kind of abstract interpretation of it to make sure that so for example, the kind of thing it checks is that by whatever path you reach a particular point in the code, you have the same types of object on the stack, so that there isn't possible to reach that point with different. So there are things going on. I think there's more things that could be done. There's an interesting development at the moment about what are called nullable types. Okay, so this notion that Tony Hoare said that he thought inventing I should have meant to put his quote in. He said that he feels guilty about inventing. Another thing he invented was the null pointer, and he said he thinks that was $1 billion mistake. He said it was too tempting to put the null pointer in, and he says that's wasted so much time. And if you'd just done recursive types properly and hadn't introduced null pointers, it would have made things life a lot easier. So what we're seeing now is languages which either have a special type system or have special annotations and tool support, which try and prove statically that things cannot be null at runtime. Okay, so they try and eliminate the runtime error statically by doing this kind of analysis. So I think these techniques are coming in, but they're kind of behind the scenes. But you know, yes, I agree with the premise that this sort of thing should be happening, but I think it is happening. But yeah, interesting.
Right, I'm going to take this one over here in just one moment. Can I just amplify what you said? The tool story is a huge thing in its own right. I happen to know that even 10 years ago, the amount of money that was being put into the development of tools like Eclipse was in the tens of millions of dollars.
Yes,
so there's a big story there, which is kind of orthogonal to the programming language story.
Yeah, exactly.
This one back here.
I was just wondering about Coral 66.
Oh, right, okay. Coral 66.
I read a manual once.
Okay, so
I'll just read a few money.
So I know very little about Coral 66. I believe it was a sort of MOD type language.
Another Marvel language.
Another Marvel language doesn't
It's
surprise
a
me.
very static version of Algol.
Yeah, Algol-ish, I would imagine, but with a bit of support for concurrency. Mascot, did it have semaphores and things like that in it?
Some low-level stuff.
Yeah. I don't know very much about it, but it was a sort of defense type language. I suspect it's not on my chart, unfortunately. We can have a look for it, but
is Jovial on there?
Jovial, I don't know.
Can't see it. Can't see it.
Anyway, have a look at it afterwards.
Yeah, come have a look. 58. A question over here.
Algol 58's there.
Yeah, well, firstly, just as a comment regarding Objective-C, I know that Objective-C was in the GNU suite in the mid-90s,
right.
Way before Apple started developing any.
Oh well, I'm not sure about. You see, remember a lot of the macOS X stuff came from the Next, so it's the next step. So the history of it is quite complex.
Yeah, maybe it has been in the background, but certainly there was no iPhone at that time.
Yeah. Oh yeah.
The main comment I was going to make though is about the generics, which I think are one of the most important developments. More recently, I don't know how far back their root may reach, but for things like Java, I think they're quite essential for the future. And I think that the current situation is very unsatisfactory, and where my gut feeling is that this might have gone wrong, because by the time they could have done the second part of the step, which might have been breaking some but with compatibility when things were just going downhill at Sun, and so therefore it's never been properly done until this day, which is really a shame.
Yes. Yeah, no, I mean, you're right. I think parameterized types, generics, whatever you want to call them, are certainly a significant thing. I don't think they were in Pascal or the they came from ML. So they presumably come from. Did they come from Dana Scott's idea about domains?
From Milner typing.
Milner type systems, yeah. So they weren't part. They definitely weren't part of the sort of Pascal. They're not mentioned in here. They're not seen as being in here. They weren't really in Simula either. I mean, Simula, because Simula kind of cheated because it had this idea that everything inherited from, you know, because it was a simulation language, everything was a kind of simulation object, and therefore inherited certain things. So they were kind of using inheritance instead of generic types. So we had it in. When did it come in? It was certainly in Eiffel. I'm not sure what were the first mainstream language that had parameterized types. I mean, but you're right. I mean, I think yes, C++ had it, but I think it was in other languages before.
Well, surely that was one of the great features of Clue, wasn't it?
Yeah. So Clue had it, right?
I don't know whether she invented it. But,
well, that's interesting. So Clue had it. So that would have been mid-70s then. But where did Clue get it from? Did he get it from ML? I don't know. Or did they invent it? Yeah, it is such an obvious idea, and of course I think and it's not just having, you know, set of X, it's having set of X with some property like being comparable. And I think the type theory behind it is it F-bounded polymorphism is actually the type theory behind it, where you have a bound on the polymorphism.
Well, again, Clue had a where T has,
yes,
and then you could list the methods as we call it today.
Okay, well, it'll be interesting to trace that back and see where it came from.
And of course, Ada had the same thing.
Yeah, but Ada was a bit later.
Again, 1980s. You could put requirements on on types.
Yeah. And yes, but that whole. So yes, two things: the type parameterization, very important development, probably wasn't there in Algol, appeared in Clue, maybe via ML, who knows. But as you say, Java, there was this backwards compatibility issue, and there's well, the other interesting thing about it was the people who designed it were people from the functional programming community. You know, quite unlikely people really who were responsible for the design of generic types in Java, and the syntax is truly bizarre. But some of it's very esoteric. I don't understand what some bits of it mean. The kind of upper and lower bounds on the types are very, very strange. But yes, I think this is this backwards compatibility problem. And once you have a lot of code, and I think this is a problem perhaps the early pioneers didn't have. Once you have a big volume of code and you're worried about binary compatibility, you are restricted in the changes you can make.
Yeah.
And that becomes a limiting factor.
Going to take two more questions. So Trevor and then Tom. And I'm sorry, we'll do the rest of the discussion with us.
Yeah.
I realise obviously that we couldn't cover anything, but there seem to be two features that you perhaps didn't mention, which are again coming quite old. Well, one is pattern matching, which started with maybe Snowball 4 even, but then obviously Prolog, but that's again been taken up a lot in Scala, Haskell, Erlang, and so on. That's now
you mean the Haskell idea of listing possible pattern matching to the
Well, and also pulling a structure apart.
Yes.
Saying what the structure you want it is to get all the bits in one go, rather than having to carve color of this and so on.
Yes, no, I agree. That's a very elegant idea, and looking at I think it goes at least as far back as Miranda and KRC. And
I think you can even map that back to decision tables.
Yeah, could you? Yeah. No, but that's a nice idea. I should have perhaps, as probably obvious, my talk was primarily around the kind of procedural type languages, not the functional languages, a whole other area. So I'm kind of aware of them, but I don't really have any deep knowledge on them.
Right. Let's just give Tom his the other way. Now let's do it in the one line, if you don't mind, Trevor, because I'm sure lots of people want to get away.
Well, just to say this, looking at what Tom Backer says, the list is essentially, it's almost the essence of the autonomic computer, because it's data structure and a program.
Yeah.
And when you look at what we do with procedural language, you see it's very difficult to, what we claim to be able to do is to write the whole text of the program all at once. And basically, we're not very good at doing that. So shouldn't we go back to the idea of putting the program together as part of the program, which is really the idea in Lisp, isn't it?
Yeah, absolutely.
So, but that doesn't seem to have gone anywhere. I mean, there are various sort of approximations to it, but it isn't really the same thing. And now you've got types and all these things, so it's different, but we haven't got a way of doing that.
Well, it's interesting. You reminded me of an anecdote I didn't cover, which was that, and I'll add the links to all of these things, our sources, I'll add the links to the final version so you can read about these things. So Paul Graham was one of the Lisp people. I don't know if he invented it, which is what my unreliable history said, but he was clearly a Lisp person. And some point in the 1990s, he got involved in a startup, which was doing some kind of e-commerce shopping application. And their secret competitive edge was that they wrote it in Lisp. Okay? And in the end, they got bought out by Yahoo. So Yahoo Stores, Yahoo's kind of virtual shopping mall thing, was written in Lisp by these two MIT guys. And they said that because, and there's actually a paper which goes into technical detail about the kind of stuff they were doing. And they were sort of using all kinds of macros and templates and custom languages and all sorts of generative techniques, which were just very natural to them as Lisp programmers, which meant they could be very agile and very rapid in adding new features. And nobody else could keep up with them. Now, I think nowadays we're seeing all of that stuff is happening in the web languages. We're seeing all these templating systems and scripting extensions and so on. But they were doing it in Lisp very early on. So I think those ideas have had some influence, and they are kind of being used in these, a lot of these web type systems. You write what appears to be, so the idea of a sort of tag language, for example, you write what looks like some declarative, you write a kind of, you write a sort of web page using some funny looking HTML, and the HTML actually is a program underneath it which kind of expands out. So there is this idea, those ideas I think are coming in, particularly in the web environment. But yeah, I agree, I think that's a good point. And the interesting thing about Lisp was a kind of machine code. Lisp was never intended to be a programming language. It was just a kind of abstract notation. They were going to have another language on top of Lisp. But they found Lisp so useful, they never really pursued the other language. They just stuck with the basic thing. Yeah. Okay, any other comments?
I think we've had a great evening.
Yeah.
Two quick notices. Please do sign the attendance sheet if you haven't before you leave. It must be somewhere at the back. And we're going to continue a sort of related debate next month with a talk on Node.js, which I know nothing about whatsoever, but I understand it's JavaScript running on the server.
Yeah.
And so do put that in your diaries as well.
Yeah.
And a great thank you to Robert.
Thank you.
And if you